Good morning, everyone. So, today we're going to discuss some problems on statistical mechanics. Most of the problems will be based on canonical ensemble and some variations here and there. In this lecture, we will discuss 5 problems which are very basic in the sense that we're going to talk about how we can calculate the probability of system being found in a particular energy state, then partition function calculation, then energy or mean energy calculation, and so on. Before we move on to the problems, now let us remind ourselves of what we learned in the previous lecture. Let's take a few minutes to recollect what is the system that we're talking about. So we are going to talk about, say, canonical ensemble. Okay. In canonical ensemble, we have a system. Okay, so we have a system. Okay, with fixed number of particles, fixed volume, and a fixed temperature. So this is typically called NVT ensemble. Okay, so the question is, what is the probability that this system can take or can be found in a particular state of energy? So the probability of the system being found in a energy state, let's say ER, okay, is, in the last lecture we obtained as, you see, P of R is, say, 1 by Z e to the minus beta ER. Okay, so here what we have seen is beta is the 1 over kBT, that's the inverse of thermal energy, and Z is the sum over all the states of this Boltzmann factor. Okay, so you sum over all the states. Okay, so so this is the partition function. Okay, so repeatedly we will be using this partition function and this probability. Okay, so here in this, let me put it this as equation number 1 and this is equation number 2. As you may have noted, in this partition function, I have not put the the question of degeneracy in energy states. So this equation number 2 can be modified in order to accommodate the degeneracy of the state as follows. So the same partition function z, okay, in terms of the degeneracy, where we incorporate the degeneracy, is, let's put it like this, g of I, or okay, let's just use the same state notation, g of R. Okay, then e to the minus beta ER. Okay, so in this we have to, what we have to remember, this is the degeneracy. Okay, and this is the our Boltzmann factor. Okay, so what we have seen is, many of the systems can have, degenerate energy states, as we have already seen in quantum mechanics also. You can have different states which give you the same energy. Okay, so that we have to take into account also. All right, so I think we are sort of ready, and one more thing that we have to remember is that, say, we have already found we have written down the expression for the prob- probability of, a system being found in a particular energy state, epsilon r. And then we also have noted the expression of partition function. Okay. Okay, so the next relevant question here is, say, what is the uh, value of average energy of the system, or say, what is the average mean energy of the system? Very simple. Okay, so since we know the probability of the energy distribution in the system, which is given by this equation 1, we can immediately write down the mean energy as follows. So the next question of relevance is the mean. Sorry. Okay, so is the mean energy. Okay, so mean energy, let's just denote by E bar, which is okay, let us not use the bar, so let's use this bracket. Is simply written, or can be written as this 1 over z summation u r e to the minus beta r. Okay, this is the state. And now these can be shown as negative del by del beta log of the partition function. Okay, so the whole thing here, this expression of mean energy, can also incorporate the degeneration. Okay, we just have to use the appropriate expression for the degeneration, but here I have written for non-degenerate case. And and next is, say, energy fluctuation. Okay, what is the error? So what is the fluctuation in the energy? Okay, this is nothing but the error. And this can also be we write like this. Okay, so this is standard RMS error, squared average minus average squared. Okay, so this turns out to be second order derivative of the logarithm of the partition function. Okay, so these are the few expressions that we have to remember while solving these problems. Okay, so now so this is another. Okay, so these are the expressions that we will be using. Okay, now let us move on to the problem. So the first problem is related to what we discussed in the last lecture regarding the n non-interacting spin systems which can align upward or downward. So let's take these spins, okay, like this. These are points, okay, representing spins. So these are n number of spins, so 1 2 3 and so on up to this is n. Okay, so each of these spin can point upward or downward. Okay. like this, for example, some random just state. Okay, so now the question we already had in the question that we had in the last lecture was, what is the entropy density of the system? And we found out that this entropy density S, which is S over N, was negative kb. Okay, then log of p log of p plus 1 minus p log of 1 minus p. Okay, so this is the expression. Now in this problem, so we are given the expression of the entropy here. So the question is, what is the value of p at which the entropy is maximum? Okay, and here the symbol that we've used, p, refers to the probability of pointing or of pointing upwards. Okay, so in the last class we had calculated only up to the expression of entropy density. Here this is like a continuation where we are asking what is the value of p at which the entropy is maximum, the probability, and p being the probability of pointing upwards. So this kind of calculation can be done straightforward. So what we have to do is we just have to calculate the as follows. Okay, so the maximum entropy is given by the following. Okay, you take a derivative of the entropy with respect to the probability, and this will be 0. Okay, this condition will give us the probability or the maximum probability. Okay, so if we take a derivative, okay, so let's do the derivative a little bit now. Okay, so you can get rid of this nkb, which is a constant anyway. So the expression looks like this. Okay, d by dp of p log p plus 1 minus p log of 1 minus p. Okay, so this is equal to 0. So this is nothing but log p, okay, plus log p plus 1 minus, okay, log of 1 minus p minus 1 equal to 0. So I've just skipped the intermediate differentiation step, just writing. So this two gets cancelled here, and what we get here is log of p by 1 minus p equal to 0. Okay, this implies our ratio, this p by 1 minus p, should be 1. Then only log of this argument is log of this function will be 0. Okay, so this will give us p to be half. Okay, so the entropy, okay, entropy is max when p is half, that is when spin or spins have the same probability of pointing upward or downwards. Okay, so this is the first problem. So we now see that for this non-interacting ising-spin model, the entropy of the system is maximum when each spin has the same probability of pointing upwards or downwards. Okay, this is for the case of non-interacting. So when we introduce the interaction, the expression will change, and that we will see at some other lecture. Now the next problem that we are going to deal with is something to do with the partition function. Okay, calculation of partition function. So the problem goes like this. So consider a system whose three energy levels are 0, epsilon and 2 epsilon. So we have a system having three energy levels, 0, epsilon and 2 epsilon. Okay, this is energy level 0, this is epsilon, and this is 2 epsilon. Okay, now and it's also said that the energy level epsilon is twofold degenerate. Okay, so g of, let me call this state 1, state 2, state 3. Okay, state 1, state 2, state 3. So state 2 has degeneracy of 2, while the remaining 2, meaning say state 1, is not degenerate. Also state 3 is also not degenerate. Okay, having state 1. Okay, so now we have a system of the following details. Okay, now how to obtain the partition function. Now recollect, we have to recall, okay, that the partition function was like this. Okay, now let me just use the subscript I to denote the state, e to the minus beta e I. Okay, and I. So ei is the energy of ith state. Okay, so now we have the expression of partition function. So what we need to do is simply plug in the values. Okay, let's do that. So z is, okay, let me call this z1 e to the minus beta e1 plus g2 e to the minus beta e2 plus g3 e to the minus beta e3. Okay, so what is the value of g1? It's 1 here. E to the minus beta e1 is 0, and the g2 degeneracy is 2, e to the minus beta, the value of e2 is epsilon, plus g3 is also 1, and e3 or epsilon 3 is twice epsilon. Okay, so maybe I will just write this as this epsilon 1, epsilon 2, this is the energy and this is the degeneracy. Okay, so now we have the expression of partition function. Just simplify, and what we have is you see, this is 1 plus 2y e to the minus beta epsilon plus, and this is e to the minus 2y beta epsilon. Okay, so this is like a plus b whole squared. Okay, so 1 plus e to the minus beta epsilon whole square. Okay, so the partition function of the system is simply 1 plus e to the minus beta epsilon whole squared. Okay, so this is how we calculate the partition function. Okay, this is the answer. So now we are done with the second problem. Now let's move on to the third problem. So it's a similar problem, but the question is different. Okay, so we have, as in the previous case, we have a system with different energy levels. Here only two levels, so let us just draw this one level and this is second level. Okay, so let's call this the first level to be energy 0, the second level to be energy E, as according to the problem. So a two level system having energy 0 and epsilon. The level 0 and the level with 0 energy is non-degenerate, so this is degeneracy 1, and the level with energy 2 is triply degenerate. Okay, so now the question is, for this system, what is the mean energy? Okay, what is the mean energy? So the question is, what is the value of mean energy? Okay, so in this problem we have to use the expression that we had in we wrote down at the beginning. So let me just get it back to it. So see here, so this is the expression of mean energy here. Okay, this one. So we'll modify it slightly. Okay, we'll modify it slightly in order to accommodate the degeneracy. Okay, so now, so let me just write down. So for this the mean energy, okay, so the expression is this. Okay, mean energy, we use the following expression of mean energy. So E as follows. Okay, summation gi epsilon I e to the minus beta ei, and here we'll write the partition function. Okay, okay, so how do we write this? Okay, now let's just put the values directly. Okay, or just let's just write it separately to make it look simple. Okay, so summation gi epsilon I e to the minus beta ei. So this is the term in the numerator, so let's just simplify it. So g1 epsilon 1 e to the minus beta e1. So since we have only two energy levels, we'll go only up to two terms in the expansion. Okay, z2 epsilon 2 e to the minus beta a2. Okay, so we'll put the values immediately. So 1 epsilon is epsilon 1 is 0 e to the minus beta to 0 plus G2 is triply degenerate, so G2 is 3 and the value of energy is epsilon into e to the minus beta epsilon. Okay, so that gives us 3 times epsilon e to the minus beta epsilon. This is a term in the numerator, okay, and the term in the denominator, which is the partition function, if you do the same expansion, so this is G1 e to the minus beta epsilon 1, G2 e to the minus beta a2. So it's after putting all the values of epsilon and G1, so what we have is so 1 times e to the minus beta into 0 plus 3 times e to the minus beta epsilon. So this gives us the value of the partition function to be 1 plus 3 times e to the minus beta epsilon 1. Okay, so therefore the expression of mean energy is simply 3 times epsilon e to the minus beta epsilon divided by 1 plus 3 e to the minus beta epsilon. Okay, so this is the required or the mean energy of the system. Okay, mean energy of the system at temperature T. Okay, so why I'm saying temperature T, because we have to remember beta is kBT. So okay, all right, so here we have already calculated the partition function, then that leads using that we also obtain the value of the mean energy as follows. Okay, this is easy. Okay, once you know what are the values of degeneracy, what are the values of energy for each level, you just plug into the expression, you get the value of the mean energy. Okay, now let's move on to the next problem, which is also based on this kind of system. Now a slightly different question. Okay, so here again we have two level system with energies epsilon and 2 epsilon. So let's just draw it. So it's always good to draw the energy levels like this. Okay, so the first energy level, let's call this epsilon 1, the value is E as given, and the second level is twice epsilon. Okay, and degeneracy values, so this G1, you see the lower level is 4-fold degenerate, that is the G1 value is 4, and the second or upper level is doubly degenerate, that is 2. Okay, so we have a system having 4-fold degeneracy and doubly degenerate energy states. Okay, now the question is, if there are n number of particles in the system, so let's just imagine we have a box. Okay, and this box some n number of particles are there. Okay, n. Okay, so each particle can take some values. Okay, and then and the total energy of the system can also be calculated if we know the value of energy of each particle. Now let me just read the question. You see, the lower level is 4-fold degenerate while the upper level is doubly degenerate. Assuming that there are n non-interacting classical particles and they are in thermodynamic equilibrium at temperature T. Okay, and we have to calculate the fraction of particles which are in the upper level. See, out of this n number of particles, certain number of particles will be in the upper state or excited state, you can call it. Okay, let's call this n2, and a certain number of particles will be in the ground state. Okay, so we have to find a fraction of particle in this. Okay, so fraction of particles in state 2. Okay, that is, we have to look at n2 divided by, and n being the total number of particles in the system. Okay, this is a fraction. So how do we proceed? That is the question. Okay, here what we have to do is, for the fraction of particle, we can use the following expression. So the fraction of particle, or simply let's just put it like this. So number of particles in state I is given by, so the number of particles in state I is as follows. You have to, multiply to the probability of, the system being found in that particular state by the total number of particles. Okay, and we have already seen that was gi e to the minus beta ei divided by our partition function. Okay, so this is how our expression of number of particles in a particular state looks like, and the fraction would be simply ni divided by n, and that leaves us a very simple expression, e to the gi e to the minus beta ei. Okay, so this leads us to the calculation of, partition function as well as this factor. So let's just put it. Okay, so here z is summation minus beta epsilon I, which is g1 e to the minus beta e1 plus g2 e to the minus beta a2, and this is the minus beta epsilon plus 2 times e to the minus 2i's beta epsilon. Okay, this is our z, and therefore the fraction of particle in the energy state denoted by I is simply this g. So the question was in upper level. Okay, the question was in upper level, which is denoted by 2, then e to the minus beta a2 divided by partition function. So that leaves us g2 is 2 e to the minus beta e2 divided by 4 times okay. So this can be further simplified to, this one by 1 plus twice e to the beta epsilon. Okay, you can just, simplify. So now we have obtained the expression of fraction of particles in an energy state denoted by I. Okay, let's just put the value of epsilon to here so that you can see directly. This is twice epsilon, twice beta epsilons. Okay, right. Now let's move on to the final problem for today, and this is also a similar problem on the calculation of fraction of number in a particular energy state. You see here the question is, we have n non-interacting distinguishable particles in a two-level system at temperature T. Okay, so it's the same problem. So we have 0 and the second level is having energy epsilon. Okay, this is epsilon, and the energies of the levels are epsilon and 0. Okay, in the high temperature limits. So now the new thing is high temperature limit. So in the high temperature limit, what is the population of particle in the level with energy epsilon? So this is the one. So what is the population n2? Okay, so what is n2 here? So g1 is 1. So since they have not mentioned anything about the degeneracy, we assume that there is no degeneracy, and it is value 1 1. Okay, g1 as well as g2 is 1. Okay, now here the problem is straightforward as we did in the last just the previous problem. The population in the the required step is that population of particles in energy level E to epsilon is given by this epsilon which is nothing but number times the probability of the system being found in this particular state. Okay, this E2. Okay, so let's just put this here directly, the value of the state, meaning this G2 E2. Okay, so if you follow the same process, what we will have is n times e to the minus beta epsilon, okay, divided by 1 plus e to the minus beta epsilon, okay, which under the high temperature, or say for kBT greater than epsilon, we can write as follows. Okay, this n2 is approximately n times 1 by 1 plus 1, or n2 is half, okay, of the total population. Okay, so you have to remember that at high temperature the number of particles will be distributed equally among the different states. Okay, or in other words, you can also say that all the different states will have same number of particles at high temperature. Okay, so we have obtained the population of the particle in the upper energy level at high temperature. Okay, so this is how we apply these basic formulas of canonical ensemble system, where we the relevant question was like, what is the probability of system being found in a particular energy state, what is the mean energy of the system, what is the population of particle in a particular energy levels, and so on, right? So we have seen how we can tackle this problem for systems, including this degeneracy in energy levels. I hope you guys will be able to solve similar problems, and these kind of problems are very common in NetGet exam. Okay, so I hope the problem solving session is very useful, and if you have question, you will write to me, or you talk to me directly in the next class, okay, when our during our interactive class. So for today, let us stop here, and I would like to say thank you, okay, and see you in the next class, okay.